US Physics Olympiad 2008 Semifinal. That semifinal consisted from 3 stages. The first stage, part A, had 4 problems. For these 4 problems there were 60 minutes. Stage 2, that was part B, there were 2 problems, and for 2 problems they had 60 minutes. And stage 3, which is part C, it was from 1 question, 1 problem. That was 20 minutes for this problem. Part A, question A1. 4 square metal plates of area big A are arranged at an even space D as shown in the diagram. Assume that A much greater than D square. Plates 1 and 4 are first connected to a voltage source of magnitude V0, with the plate 1 positive. Plates 2 and 3 are then connected together with a wire. The wire is subsequently removed. Finally, the voltage source attached between plates 1 and 4 is replaced with a wire. The steps are summarized in the diagrams. Find the resulting potential difference V12 between plates 1 and 2. Likewise, find V23 and V34 defined similarly. Assume in each case that a positive potential difference means that the top plate is at a higher potential than a bottom plate. Solution. This problem could be solved using different approaches. One approach is to represent this figure as 3 capacitors, equal capacitors connected in series, like between these plates, and these plates. But here we will use other approach. We will use electric field between plates. So first of all, we have this thing that potential difference between first and last plate is V0, and because third and second plate are connected, potential difference between them is 0. It means that the electric field between them is 0. Remaining is electric field between the first and second plate and between third and fourth plate. Due to absolute symmetry, this electric field will be equal, and we can show it on the picture. So we have this diagram that here we have electric field E0, and here we have electric field E0. So now we can find what is this electric field. We have this equation. We multiply electric field by distance, that's 2d, and that will be voltage V0. This is how to find E0. Now let's move further. We can replace this picture by other picture, and showing how is how are charges distributed between plates. We have charge sigma 1 on the first plate, and due to symmetry, negative charge negative sigma 1 on the last plate. And because these charges they compensate each other between the second and third plate, this charge must have density negative sigma 1, and this charge is positive sigma 1. And this charge sigma 1 and negative sigma 1, they create electric field E0. And for same reason, this charge and this charge, they create between them electric field negative E0. Now let's write the last picture when we connect first and last plates. So this is the picture. Now we know that charge negative sigma 1 and sigma 1 create electric field negative E0. It means that we can write that E2 created by these plates, second and third, it's negative E0. And the plates first and last one, they create between them electric field E1. We don't know yet what it is, but we can calculate what is total potential difference created by all plates. That will be 0, because this and this connected, but from other hand we have this equation. Potential difference between first and last one, that will be 3E1 multiplied by D plus E2 multiplied by D, and that's equal 0. And we know that E2 equal negative E0, and from here we can find that electric field E1 equal E0 over 3, or due to this it's equal voltage V0 over 6D. And now we can immediately find what is a potential difference between first and second plate. That will be this one. So we have V12 equal V0 over 6, and due to symmetry it's the same as for V34 between third and fourth plates. And last step is to count what is potential difference between plate 2 and 3. To make this total potential difference 0, it must be equal negative V0 over 3. So that's the answer. Between first and second plates we have potential difference V0 over 6, same as between number 3 and number 4. And potential difference between second and third, that will be negative V0 over 3. Problem number A2 from part A. A simple heat engine consists of a movable piston in a cylinder filled with an ideal monoatomic gas. Initially the gas in the cylinder is at pressure P0 and volume V0. The gas is slowly heated at constant volume. Once the pressure reached 32 P0, piston is released, allowing the gas to expand so that no heat either enters or escapes the gas as the piston moves. Once the pressure has returned to P0, the outside of the cylinder is cooled back to the original temperature, keeping the pressure constant. For the monatomic ideal gas, you should assume that the molar heat capacity at constant volume is given by Cv equal 3 over 2R, where R is the ideal gas constant. You may express your answer in fractional form of as decimals. If you choose decimals, keep 3 significant figures in your calculations. The diagram below is now necessarily drawn to scale. Questions. A. Let V maximum be the maximum volume achieved by the gas during the cycle. What is V maximum? in terms of V0. If you are unable to solve this part of problem, you may express your answer to the remaining parts in terms of V maximum without further loss of points. Question B. In terms of P0 and V0, determine the heat added to the gas during a complete cycle. C. In terms of P0 and V0, determine the heat removed from the gas during a complete cycle. D. What is the efficiency of this cycle? Solution. This problem connected to gas laws, and usually we use so-called VP diagrams to solve problems. First question. Let V maximum be the maximum volume achieved by the gas during the cycle. What is V maximum in terms of V0? Here we have three processes. First process with a constant volume, we call it isobaric. During this process, pressure proportional to temperature. Second process is without heat transfers from outside or inside, and we call this process adiabatic process. And for this adiabatic process we have a formula, this one, where gamma is a constant for monatomic gas. It's equal to 5/3, which can be found from this expression. We have gamma equal Cp over Cv, and the Cp equal 5/2r, and the Cv equal 3/2r. Totally it's 5/3. Also, during this all processes we use universal gas law, which looks like this. And last process is from 3 to 1. It is going with a constant pressure. That's isobaric compression. Here volume proportional to temperature. We can solve this problem using a special table like this. Just count what is pressure, volume and temperature in any point. So first question, we have process from 2 to 3, adiabatic process. So we use this formula, and from here when we use numbers for gamma, P2, V2 and P3, we can count what is V3. We know that P2 equal 32 P0 and P3 equal P0, and V2 equal V0. So totally, when we put all these numbers, we will get just 8 V0. That's the answer for the first question. Next question, determine in terms of PV and P0 and V0, determine the heat added to the gas during a complete cycle. If we analyze this all three processes, heat added only during process from 1 to 2. That's isobaric heating. So it means that here we have Cv constant for heating, and we can count what is total heat added to this process. And from other hand, from 3 to 1 we have temperatures going down with a constant pressure. So it means that here we have heat capacitance equal Cp, not Cv. And we can use all these formulas without temperature. Even we don't need this table. So we can leave only this part, V3 equal 8V0. Let's count what is Q in, what is heat added during a process from 1 to 2. This is total formula. Q in equal number of moles in this gas multiplied by heat capacitance with the constant volume, which is Cv, and multiplied by temperature difference. Also, we can rewrite this in form of n multiplied by 3 over 2r, where 3 over 2r, that's heat capacitance with the constant V. But also, when we look at this formula, we have nr multiplied by r and multiplied by T2 minus T1. Using this universal gas law, we can put, instead of temperature, we can put PV, and we have this expression that all this equal to 3 over 2 32 P0 V0 minus P0 V0, which is 93 over 2 P0 V0. That will be total heat added to during this process. With the same logic, we can count what is total heat out during process from 3 over 1. So this is the procedure. Here we can count what is total heat out in the process from 3 to 1. We multiply number of moles multiplied by heat capacitance with the constant pressure, which is 5 over 2r, and multiplied by temperature difference, T3 minus T1. Using the same law, gas law, universal gas law, we can input P3 and V3 here, and P1 and V1, and that will be 8 P0 V0 minus P0 V0, and finally we will get 35 over 2 P0 V0. That's our heat out. That's answer for question C. And last question is what is efficiency of this cycle, and efficiency for this cycle could be found from this expression. Part A, problem A3. A certain planet of radius big R is composed of a uniform material that, through radioactive decay, generates net power big P. This results in a temperature difference between the inside and outside of the planet as heat is transferred from the interior to the surface. The rate of heat transfer is governed by the thermal conductivity. The thermal conductivity of a material is measured of how quickly heat flows through that material in response to a temperature gradient. Specifically, consider a thin slab of material of area A and thickness delta x, where one surface is hotter than the other by an amount of delta big T, delta temperature. Suppose that an amount of heat, delta Q, flows from the slab in a time delta T. The thermal conductivity K of the material is then K equal delta Q over delta T multiplied by 1 over A area and multiplied by dx over dt. It is found that K is approximately constant for many materials. Assume that it is a constant for the planet. For the following, assume that the planet is in a steady state. Temperature might depend on position, but does not depend on time. So, first question. Find an expression for the temperature of the surface of the planet assuming black body radiation and a emissivity of 1 and no radiation incident on the planet surface. You may express your answer in terms of any of the following variables and the Stefan-Boltzmann constant sigma. Question B. Find an expression for the temperature difference between the surface of the planet and the center of the planet. You may express your answer in terms of any of the above variables. You do not need to answer part A to be able to answer this part. Question A. Find an expression for the temperature of the surface of the planet assuming black body radiation. According to formula Boltzmann, we have power proportional to temperature power 4, this one, where sigma is Boltzmann constant and A it's area and T is temperature, absolute temperature. And now from this formula we can immediately find what is the temperature of this planet. This is the expression. We have 4 pi r squared, that's the area on the surface of this planet. And this is the answer for question A. Question B. Find an expression for the temperature difference between the surface of the planet and the center of the planet. Now let's assume that delta Q over delta T, it's a radiation created in any part of planet with the same density. So it means that radiation proportional to volume. If we take a sphere of radius small r, we can count what is radiation created by this small sphere, and it's proportional to r cube. So it means that we know what is dq over dt, and we can put it here. And also we know what is area of this small sphere, and we can rewrite this formula in form of, and after splitting variables we have this formula: delta T, delta temperature equal power over 4 pi k big R cube multiplied by R dr. And after integration we can find what is a temperature difference. That will be this one. On the left side we have temperature difference, and on the right side we integrate from 0 to big R. So that's the answer for question B. Part A, problem A4. A tape recorder playing a single tone of frequency F0 is dropped from rest at height h. You stand directly underneath the tape recorder and measure the frequency observed as a function of time. Here t equals 0 seconds is the time at which the tape recorder was dropped. The acceleration due to gravity is g equal 9.8 meters per second square, and the speed of sound in air is 340 meters per second. Ignore air resistance. You might need to use the Doppler shift formula for so-called motion of source and the observers in still air. this is the formula, where F0 is the emitted frequency as determined by the source, F is the frequency as detected by the observer, and V sound, V source and V observer are the speed of sound, in air the speed of source and the speed of the observer. The positive and negative signs are dependent upon the relative directions of the motions of the source and the observer. Questions. A. Determine the frequency measured on the ground at time t in terms of F0, G, H and V sound. Consider only the case where the falling tape recorder doesn't exceed the speed of sound. B. Verify graphically that your result is consistent with the provided data. C. What numerically is the frequency played by the tape recorder? D. From what height h was the tape recorder dropped? Solution. First of all, we cannot use a directly Doppler effect here because the source moving with a not constant speed. The speed is always increasing, and it means that in time t we are catching sound which are coming from source emitted in time t prime. And in that case we can use formula total height equal total distance traveled by source, which is 1/2 g t prime square plus distance traveled by sound after that, which is v sound multiplied by t minus t prime. So we have to solve this quadratic equation. Let's rewrite it in better form. And now solution will be for t prime, this one. We see that we have two roots, plus and minus. Let's see what happened. For example, we have to investigate if t prime is correct for plus or minus. Let's take a look at this table. After time t equal only 2 seconds, the sound already reached us, and for this time source traveled just a very small, very short distance. So it means that our building almost like about more than about 600 meters tall. And look at this formula. Here we have v sound square plus this 2gh minus 2g v sound t. So for time v sound t, this sound travel always almost height h. It means that here we have negative expression. So we have v sound square minus something very small negative. So it means that we have to subtract from v sound this part which is a little less than v sound. In that case v prime will be small, which is consistent, because it must be small. But if we put here positive, that will be 2 v sound over g, which is quite big. So it cannot be right. So the correct root will be with negative sign. And now let's use a Doppler formula, where we have to use time t prime, not time t. In that case, this Doppler formula look like this. We have zero speed of observer. It means that on the numerator we have only speed of sound, and denominator we have speed of sound minus speed of our source, in which it was time t prime. So that will be g t prime, speed of this source. And now we can put this time t prime to this formula, which will give us this expression. Now we have expression for frequency in terms of f0, v sound, g, h, and time. And this will be answer for the question A. Second question B. We have to graphically verify results from this table. Best way to do it is to represent this dependency as a linear function. In that case, we have to square both parts and reverse them, and we will get this expression. That's a linear function. We have already numbers for frequency. We can put it here, and we have time. So hopefully this function will look like linear function. Let's draw this graph. That will be our table for this graph. We have 1 over f squared, the function of time. And from this graph we can find what is the slope of this graph. That will be negative 1.75, 10 power negative 7 seconds in power negative 1. And after that use this expression to find what is f0, this expression. After, when we put numbers, we will get answer 574 Hertz. And the last step to find what is total height for this building, using again this expression. And we have, after that we can find the intercept for this graph from this equation. We can put intercept equal to this expression, and the intercept for this graph equal 3.31 10 power negative 6 seconds square. And after that we can find what is total height. These are our final calculations. We can use this formula to calculate what is total height. That will be 533 meters. Part B, problem B1. A platform is attached to the ground by an ideal spring of constant K. Both the spring and the platform have negligible mass. Assume that your mass is mp. Sitting on the platform is a rather large lump of clay of mass mc equal rmp, where r is some positive constant that measures the ratio mc over mp. You then gently step onto the platform, and the platform settles down to a new equilibrium position, a vertical distance d below the original position. Throughout the problem, assume that you never lose contact with the platform. Questions. A. You then slowly pick up the lump of clay and hold it at height h above the platform Upon releasing the clay, you and the platform will oscillate up and down. You notice that the clay strikes the platform after the platform has completed exactly one oscillation. Determine the numerical value of the ratio h/d. B. Assume the resulting collision between the clay and the platform is completely inelastic. Find the ratio of the amplitude of the oscillation of the platform after the collision, AF, to the amplitude of the oscillations of the platform before the collision, AI. Determine a ratio AF over AI in terms of the mass ratio R and any necessary numerical constants. C. Sketch a graph of the position of the platform as a function of time with a t equals 0 corresponding to the moment when the clay is dropped. Shown one complete oscillation after the clay has collided with the platform. It is not necessary to use graph paper. D. The above experiment is only possible if the mass ratio R is less than some critical value Rc. Otherwise, despite the clay having been dropped from the height determined in part A, the oscillating platform will hit the clay before the platform has completed one full oscillation. On your graph in part C, sketch the position of the clay as a function of time relative to the position of the platform for the mass ratio R equal Rc. Question A. You then slowly pick up the lump of clay and hold it a height h above the platform. Upon releasing the clay, you and the platform will oscillate up and down. You notice that the clay strikes the platform after the platform has completed exactly one oscillation. Determine the numerical value of the ratio h over d. So first let's write equation connecting distance d, big D, and other parameters. So we have kd equal mp multiplied by g. This is from our first assumption. And after that we can count that constant k equal mpg over d. Second thing, because we already know what is this equation, we can find what is omega for this oscillation. That will be square root from k over mp. And now we can find the full period for this oscillation. This is the expression for full period. And for the same period, our clay start to fall down and reach the lowest point from where we start our oscillation. We did oscillation from lowest point somewhere to this lowest point. It means that our clay reach distance h for the same period of time. So we have this equation. From one hand we have h equal 1/2 gt square, and when we put t expression for period, we will have this expression, and after that we will put k as this relation, and we have finally this answer, h over d equal 2 pi square. Question B. Assume the resulting collision between the clay and the platform is completely inelastic. Find the ratio of the amplitude of the oscillation of the platform after the collision AF to the amplitude of the oscillations of the platform before the collision AI. Determine AF over AI in terms of the mass ratio R and any necessary numerical constants. First of all, we can find what is the new equilibrium position for the first oscillation, because this oscillation stop right in on a distance d. So first of all, we can count what is amplitude for the first oscillation before collision, because if this fellow reached the lowest point, it means that it has a maximum displacement from new equilibrium. But new equilibrium now we can find from a force of gravity which created by a piece of clay, because before the equilibrium position was right in this point, and now it must go higher on a distance, this one, where mc it's a mass of piece of clay, mg that's extra force of gravity, so it means that it must be equal to k multiplied by ai, where ai is this amplitude for this oscillation, because it's oscillate between lowest point and the point of equilibrium, which is higher on this distance ai. So from here we can count what is ai. This is the expression. So second step. Now let's see what happens when clay is heating us in the lowest point. When it's heating in the lowest point, it means that now we have the same mass as in the beginning. So it means that in the lowest point now is the equilibrium point for our second oscillation. And now we can count what is total kinetic energy from this point, because this piece of clay heat us, and we can count what is total speed, initial speed in this position. For that we have to count first what is the speed of this piece of clay right before collision. This could be found from formula Vc square equal 2gh, where Vc, where h is distance traveled by this piece of clay before it hit this platform. So it means that Vc equal this expression. Now we have a completely inelastic collision with the platform, so we can count what is speed of platform right after collision. We just use momentum conservation. So previous momentum mcvc, that was equal new momentum mc plus mp multiplied by our speed after collision. And now we can count what is this speed. That's this expression. And the last step is we can find what is total kinetic energy in this position and equalize it to potential energy of our oscillation in a point of amplitude. So we have this expression. This is our kinetic energy going to potential energy for spring with the amplitude with a new amplitude AF. Now we can count what is a new amplitude. We have this expression, and the amplitude, it will be this one. Now we can count what is the relation between final and initial amplitude. So we have to divide this expression by this expression, and we will get this formula. So we have to exclude constant k, but we remember that constant k was first found from this k equal mpg over d. So we can substantiate it here, and we have this expression. Also we have h over d we already counted. That was this one, and finally we will get this formula, and totally this is the our answer: 2 pi over root from 1 plus r, where r is coefficient between mc and mp. So that's the solution for question B. Question C. Sketch the graph of the position of the platform as a function of time, with the t equals 0 corresponding to the moment when the clay is dropped. Show one complete oscillation after the clay has collided with the platform. It is not necessary to use graph paper. So let's see. If we have a very small amplitude for platform oscillation, this graph looks like this, and we see that clay will never cross a platform before lowest position. But suppose that we have a big amplitude for this platform. So in that case we can draw this picture, and we see if for example if this parabola from clay cross this first time cross sine function from platform in top position, it must cross it again second time somewhere before it crossing third time in the lowest position. Let's count what happens if this clay crossing platform in the highest position. Highest position, it means that platform moved for half period, and for this half period that was half time for clay to drop. It means that clay reach a height only 3 over 4 h, and if this is height 3 over 4 h, it means that amplitude for platform will be 3 over 8 h. But from other hand, we already counted that amplitude initial equal this expression, and the spring constant was this expression. And also for our case we had this relation. Now let's combine all this stuff. We can insert in this formula k and use relation h over d, so we will get this thing. So we have amplitude for a platform equal rd, and now we can equalize it to 3 over 8 h. That will be this one. It means that r equal 3 over 8 h over d, but h over d equal 2 pi square. So finally we will get this answer. So it means that for relation between mass of clay and mass of platform equal to 3 over 4 pi square, first time clay will meet a platform in the highest position. After that it will cross platform somewhere, and later it will meet in lowest point platform. So we see that for small amplitude, for very small relation between mass of clay and mass of platform, they will never meet before lowest position. For big rate they will meet 3 times, so it means somewhere between this parabola, it will just touch this sine function, and that's a critical relation between mass of clay and mass of platform. So it exists. Part B, problem B2, second problem of 2 problems in this section. Consider a parallel plate capacitor with the plates vertical. The plates of the capacitor are rigidly supported in space. The distance between the plates is d small. The plates have a height h and area A big, much greater than d square. Assume throughout this problem that the force of air resistance may be neglected. However, the force of gravity cannot be neglected. Neglect any H effects as well as any magnetic effects. Section A. A small metal ball with a mass big M and a charge Q is suspended from a string of length L that is tied to a rigid support. When the capacitor is not charged, the metal ball is located at the center of the capacitor at distance d/2 from both plates and at a height h/2 above the bottom edge of the plates. If instead a constant potential difference V0 is applied across the plates, the string will make an angle θ0 to the vertical when the metal ball is in equilibrium. First, determine θ0 in terms of the given quantities and the fundamental constants. Second, the metal ball is then lifted until it makes an angle θ to the vertical, where θ is only slightly greater than θ0. The metal ball is then released from rest. Show that the resulting motion is a simple harmonic motion, and find the period of the oscillations in terms of the given quantities and the fundamental constants. Third, when the ball is at rest in the equilibrium position Q0, the string is cut. What is the maximum value for V0 so that the ball will not hit one of the plates before exiting? Express your answer in terms of the given quantities and the fundamental constants. First, let's draw the picture showing forces acting on this ball. So we have mg, which is a force of gravity, vertical force, and we have force horizontal, Q multiplied by V0 divided by D, where V0 over D, that's the electric field, and field multiplied by charge, that's a force. So from this picture we can immediately find that tangent θ0 equal this expression, QV0 over dmg. That's the answer for the first question. Second question. The metal ball is then lifted until it makes an angle θ to the vertical, where θ is only slightly greater than θ0. The metal ball is then released from rest. Show that the resulting motion is a simple harmonic motion, and find the period of the oscillations in terms of the given quantities and the fundamental constants. So first of all, if we apply additionally to gravity force electric force, we have a new force and the angle θ0 acting on this ball, and we can assume that this new net force acting like a new gravity force, and we can find g prime gravity acceleration for this force. Force could be found from this equation. This is just pure geometry, because both forces are perpendicular to each other, and effective gravity acceleration for this case equal g prime equal force divided by mass, which is this expression. And last thing is we can find what is a period for pendulum with length L, and gravity acceleration of free fall. In our case it's a g prime. Period will be 2 pi L over g prime, and now we can substitute a g prime here and find what is total period. So period will be this expression, 2 pi and root 4 from L square over g square plus qv0 over dm square. So that's done. So we can write this answer in form of this one, or better this one. So that's the answer for question 2. Question 3. When the ball is at rest in the equilibrium position θ0, the string is cut. What is the maximum value for V0 so that the ball will not hit one of the plates before exiting? Express your answer in terms of the given quantities and the fundamental constants. So first let's draw this picture. We have on this picture we have angle θ0 between the vertical and the direction of string, and we see that if this tangent of this angle exceed d over 2 divided by L plus h over 2, this ball will hit this plate. So it means that we have to make this inequality. So tangent theta must be less than d over 2 divided by L plus h over 2. But tangent theta we already counted, this one, and after we insert this tangent we can get this inequality. So it means that V0 must be less than this expression. That's the answer for third question. Question B. Suppose instead that the ball of mass m and the charge q is released from rest at a point halfway between the plates at a time t equals 0. Now AC potential difference V as a function of t equal V0 sine omega t is also placed across the capacitor. The ball may hit one of the plates before it falls under the influence of gravity out of the region between the plates. If V0 is sufficiently large, this will only occur for some range of an angular frequency omega minimum less than omega maximum. You may assume that omega minimum much less than square root from g over h, and omega maximum much greater than square root from g over h. Making these assumptions, find expressions for omega minimum and omega maximum in terms of the given quantities and or fundamental constants. Solution. We have potential difference as a function of time. It means that we can count what is the horizontal force on this ball, and by integrating we can find what is speed, and after that what is displacement, horizontal displacement. So first of all we can write expression for acceleration. This is our acceleration. That's force q v0 over d divided by mass and multiplied by sine omega t. First we can integrate this formula to find what is formula for speed. That will be this one. Here we use knowledge that the initial speed is 0. It means that cosine omega t is 1 and the total is 0. This is how to find constant for integration. Second, we can integrate this formula again and find what is horizontal displacement. That will be this one. Again, when time equal 0, we have displacement is 0. Now let's count what is time to travel, because we have free fall in the vertical direction and we have this formula, and time will be total time to travel. So now let's examine our conditions. First condition, when omega is much larger than this expression, it means that period will be much less than total time to travel. It means that in this formula 1 over omega will be much less than total final time, and we can neglect this member, and we can leave only time t here and neglect the right expression. So we have total distance is this one, and now we can estimate that this distance must be less than d over 2. We have d over 2 greater than this expression on the right side, and from this inequality we can find what is our omega, which must be greater than something. In that case we have omega, if omega greater than this expression, which we can call omega maximum, this ball will never hit the plate, but if it's less, that will hit this plate. Let's count other possibility when omega is very small. If omega is very small, it means that this sign could be represented in this form. So for small omega t, we have this approximate expression for sine omega t. We will get this expression for x, and now we can put here expression for time, and we have for displacement we have this expression. But if we don't want to hit this plate, x must be less than d over 2. It means that we have this inequality, and finally we can find that omega must be less than omega minimum, which is this one. So we found that if omega less than this expression, which we can call omega minimum, we will not hit this plate. So that's the answer for question B. Part C. That was one question for this part, one problem. Optical Society of America bonus question. Researchers have developed a lens made of liquid. The spherical lens consists of a droplet of transparent liquid resting on an electrically controllable surface. When the voltage of the surface is changed, the droplet itself changes shape. It either tries to ball up more strongly or it becomes flatter. The figure below is a sketch of the liquid lens and several parameters that describe it, including the thickness of the lens T, the radius of curvature of the top surface R, and the contact angle theta, which represents the angle between the flat surface beneath the droplet and the tangent to the curved surface at the point of contact. There are 6 questions for this part. Question A. When a certain voltage is applied, both the contact angle and the lens thickness increase and the lens become more curved. In this case, is the liquid attracted or repelled by the surface? Question B. Express the contact angle as a function of radius r and thickness t. C. The total volume of the liquid lens is an important parameter because as the liquid lens changes shape, its volume is conserved. Calculate the volume of the lens as a function of the radius and the thickness t. D. Use your result to part B to eliminate the variable t from your expression for the volume and find the volume as a function of radius and theta. E. By changing the voltage on the control surface, the contact angle theta can be changed, which in turn changes the focal length of the lens. F. The lens maker's formula can be used to calculate the focal length and is given by formula 1 over F equal N liquid minus N air multiplied by 1 over R1 minus 1 over R2, where N liquid and N air are the refractive indices of the liquid in the lens and the air around it, and the R1 and R2 are the radii of curvature of the two surfaces of the lenses. In figure, R1 is the curved face and R2 is the flat face. Use the lens maker's formula to calculate the focal length of the lens in terms of the total volume of the liquid, the contact angle, and the relevant refractive indices. Side note: liquid lenses are interesting because they are electrically controllable, variable focus lenses that can be very compact. People are working on putting them into cell phones, cameras for ultra-compact zoom lenses. Question A. When a certain voltage is applied, both the contact angle and the lens thickness increase, and the lens becomes more curved. In this case, is the liquid attracted or repelled by the surface? Answer. When curve is increased and angle increased, this droplet will go up. It means that it's going against gravity. It means that voltage will repel this droplet. That's the answer. B. Express the contact angle as a function of radius r and the thickness t. Answer. From geometry we see that this angle theta equal this angle theta because of perpendicular sides for both. And from geometry we see that this side equal r minus t, and this will be cateted, and this is hypotenuse r. So it means that cosine theta will be this expression r minus t over r, or 1 minus t over r. That's the answer for part B. Question C. The total volume of the liquid lens is an important parameter, because as the liquid lens changes shape, its volume is conserved. Calculate the volume of the lens as a function of r and t. To calculate volume, we have to put this picture on our xy graph. Suppose that y starts in the center of this circle, and y direction is straight up. So it means that top will be when y equal r. And we have to integrate our cross-section, area of cross-section by y direction. So on a distance y from the center of this sphere, we have expression for radius. Radius of this circle equal r square minus y square. So it means that we can count what is area by multiplying this radius by pi. And finally we have this result. Volume equal integral from pi r square dy, and limits are from r minus t to r. You can see it from this picture. So instead of small r square, we can insert r square minus y square, and we have this integral. And now result will be pi r square y minus 1/3 y cube, and the limits are from r to r minus t. When we insert these limits, we have this one, and after calculation, this is a final result for volume. This is how to express volume using radius and thickness of this lens. Next question, D. Use your result to part B, variable t, from your expression for the volume, and find volume as a function of radius and theta. In part B, we already found that cosine theta equal 1 minus t over r. From this formula, we can find that t could be expressed through radius and theta this way. Thickness t equal r multiplied by 1 minus cosine theta. And now we can substantiate this t to formula for volume through radius and t. That will be this expression. And now we can combine these results and finally get this expression. Volume equal 1/3 pi r cube multiplied by 2 minus cosine theta and multiplied by 1 minus cosine theta square. That's the answer for question D. Question E. By changing the voltage on the control surface, the contact angle theta can be changed, which in turn changes the focal length of the lens f. The lens maker's formula can be used to calculate the focal length and is given by formula 1 over f equal n liquid minus n air multiplied by 1 over r1 minus 1 over r2, where n liquid and n air are the refractive indices of the liquid in the lens and the air around it, and r1 and r2 are the radii of curvature of the two surfaces of the lens. In figure, r1 is a curved face, which is r, and r2 is the flat face, where r2 equal infinity. Use the lens maker's formula to calculate the focal length of the lens in terms of the total volume of the liquid, the contact angle, and the relevant surface indices. Answer. This formula, lens maker's formula, we can rewrite in form of this one, because r2 equal infinity and 1 over r2 equals 0. So this is the expression for focal distance for a lens. And now we can express our radius through volume. For that we use this formula. Volume equal 1/3 pi r cube multiplied by this expression. And we can represent r through volume. That will be this numerator if we do proper calculations. And final answer will be like this. That's the answer for question E.